I promise you that I will show that for primary operators, or tensor fields, the OPE with the stress energy tensor contain only two singular terms. And so in order to derive this, so the derivation is really analogous to what we did before. So except that we consider a transformation, again, I'm just concentrating on holomorphic one, when z goes to z plus epsilon b of z. And so I'm asking the question, how does my field transform? So I have O prime of z prime is going to be equal to z plus epsilon b to the power minus h, right? And then I have O of z, and so here, yeah, actually I have to take a derivative with respect to that, so this gives me 1 plus epsilon del b to the power minus ho. And so this equals to 1, so it equals to O plus, minus epsilon h del b times O. So everything is parallel except it would be exactly the same if I were to choose v equals to that. And so in this case, just literally repeating what we did before, the transformation will be O minus epsilon h del b times O. And then there is additional shift due to the fact that we are in z prime coordinate instead of z. So that's epsilon b times del O. Okay. There is a subtle difference between my O and B. And then I have to subtract O. And so this equals to minus epsilon b times O of 0 minus epsilon b epsilon del b times O of 1. Because we did this transformation with arbitrary function, there is no extra terms in this transformation. And so what we are finding is that O0 equals to O0 equals to del O, right? And O1.
I think you missed an edge.
Sorry?
You missed an edge somewhere?
Yes. No, I didn't, because here I wrote it epsilon b O1, epsilon del b O0, right? So I'm writing it in I'm writing it in this form. So it's 1 over n factorial derivatives of v times operators that come with OPs, right? That's this index n. Right? So now what I'm doing, I'm actually comparing this line with the exact transformation law that we found, and I'm finding that this operator O0 is derivative of the operator O, and operator O1 is H times an operator O. So, and once you have this, and actually all the other guys, Q and so on, those operators vanish, and the reason they vanish is because there are no del k v terms in the transformation problem. So there's only del v and v for arbitrary function. Okay, so given this, we immediately conclude this OPE, so it's h over z squared times O plus 1 over z del O plus not c. Okay? So now we can go ahead and collect what we learned before. we considered various fields, and so let's ask the question, are those fields that we considered primary fields, or are they tensor operators? So what we do is consider weights of some operators. Okay. So what we did before, we evaluated this OPE, and so we showed that a singular piece takes this form. So it's 1 over z del of x mu. Okay, and then there were non-singular terms, and so you can see that that's exactly what's needed for operator. So our x mu has a holomorphic weight 0, right? So h tilde for this is 0, and you can do an anti-holomorphic, and you will find 0 as well. Okay. Notice again that it's guaranteed that the coefficient multiplying 1 over z in the OPE will always be a derivative of the operator itself. Okay. So right. So and if I'm asking the question, what are the OPE? What are the weights of operator del x? Well, so we know that this guy is 1, 0, del 2x. So this guy has 2, 0. Simply using the properties that we established before, that once we act with a del on an operator of a given scaling weight, so we'll simply increase corresponding the holomorphic or anti-holomorphic weight. So those are simple examples, but then there is one that's less trivial, and this is an operator O, which is e to the I kx, right? So this is an operator that I kept promising you will be related to the emission of tachyons in our Boswellia string theory. And so what we want to do, we want to compute the weight. So find the weight of this operator. It will be important for us later. And so in order to do that, so we have to look at the OPE of the stress energy tensor with this operator. And so the OPE, if it is a nice happy operator, happy primary field, so it must be of this form times O plus a leading term. So in other words, what we need to do when we look at our OPE, we need to look carefully at the largest singular piece. And so let's just do this computation. So I have -1 over alpha prime, and the stress energy times the del x mu, right? And it acts on e to the I kx. Okay. So again, the more cross contractions you do, the more singular piece you will get. So in this case, in order to get the most singular piece, I need to make 2 cross contractions. So I will have -1 over alpha prime. So that's the factor there. Now, I'm taking cross contractions. So I'm going to bring 2 factors of alpha prime over 2. And there is a 1 over 2 factorial, right? That's when I expand this cross contraction functional differential. And then there will be 2 logs. So it's value of z squared, and then another one. Because there will be 2 pairs of del over del x, right? So for each pair, what will happen is that 1 over del over del x acts on these guys. The other one will act on the on the exponential. So the ones that act on these fields will produce a derivative of the law, right? So is that clear? I'm assuming that you need some reading. I mean, looked at the lecture before, so you're comfortable with me just mentioning things. So that's when we do when we act with Delaware. So this guy will obtain when we act with Del over Del as what we call it as subscript f. And there is only one derivative acting on these log functions because it comes from this derivative here. Now there is a symmetry factor, right? So the symmetry factor is 2 because when I act with the first one, I have a choice whether I will act on the first axis or on the second one. And so the symmetry factor is 2. Okay? So remember in cross contraction, there was also del over del x g, which was acting on the second operator. And so if that guy acts on the second operator, the only thing it will do, it will bring down e to the ikx, and it will leave the operator unchanged. So I'm going to write it down. So I will have I k mu times I k mu, and then I have e to the I kx left. Okay? So that's the only thing that we have. So there will be 2 del over del xj. Okay, so now we have this general expression, and you see immediately that the most singular piece will be 1 over z squared, and it's going to be multiplying the operator itself, much like predicted for the primary field. And so what we will find out that guy actually is equal to k squared over alpha prime squared over 4, 1 over z squared e to the I kx plus some leading pieces. And so we expect this guy to be of the form h divided by z squared, right, times an operator itself plus some leading pieces. And so just looking at 2 expressions, you find out that h equals k squared alpha prime divided by 4. And so similarly, h tilde is going to be equal k squared alpha prime divided by 4. Okay, so is it clear? Now you know how, actually if you go ahead and we extracted only 1 over z squared, and if you are careful and look at the subleading term, something that I will do in a slightly different example, you actually extract the piece 1 over derivative of the operator. So it's indeed, we have to say that this operator e to the I k x is a primary field. Is a primary field of weights k squared alpha prime over 4, k squared alpha prime over 4. So I told you that this operator in the CFT will correspond to the addition of tachyon, but all of us hate tachyon, okay? And we want something much more reasonable, like emission of graviton, and see how the string theory computes the cross-section of those. So running much ahead, what I want to say is that emission of high excited states, and in particular compared to tachyon, graviton will be an excited state, corresponds to operators when we dress up this tachyonic vertex, tachyonic operator with derivatives of del x. So in particular, in general, we will be interested in operators of this type. So product of J, del bar, and J, x, and J, and then e to the I, k, x. And so this operator, we can go ahead and compute the weights of this operator, but we can do it much simpler. Okay, so, we simply notice that axis itself doesn't carry any weight. And derivatives, every time we act with derivative, increase weight by 1 unit. So this guy has weight k squared alpha prime 4 plus sum over mi, and the anti-holomorphic weight plus sum over nj. Okay. So these summations ni and aj simply counts the number of derivatives. So any questions?
There's a very naive question.
Yep.
I learned some complex manifold a long time ago.
Yep.
I couldn't remember very clearly. But the pair H2 looks
Yep. Hodge numbers, no, they're unrelated. Okay, so go ahead. Right, so the only field that somehow I was omitting to discuss was the stress energy terms, right? So I said, look, all those are nice operators, but we all kind of want the stress energy tensor to be the nicest operator of them all. And unfortunately, that's not the case. And so what we're doing now are discussing conformal properties of the stress energy tensor. So what's the story there? Well, it turns out that, remember we did a computation of the following type. So we computed the OP of del x mu, del x mu, del x mu, del x mu. So we computed this contraction before, and I told you, ask me the question because we will use that result somewhere later. And so now is the time to use this result. So you can see that this is up to a constant t of z, and this is t, say, t of 0. And so in fact, when we played around with contractions of operators, we already computed their contraction, the contractions relevant here, and that gave us the OP of the stress energy tensor with itself. And so what we found that there is a more singular piece. It goes like d. D, remember, is the number of scalar fields divided by 2z to the fourth plus 2 over z squared, the stress energy tensor, plus 1 over z del t plus non-singular. Okay? So if you look at this formula and you say, well, it's almost a primary field, right? So for a primary field, we need operator plus 1 over z, the derivative of this operator. So this piece looks like that the stress energy tensor T would be of weights 2 and 0. But the problem is this piece. Okay, so this piece, whenever we have some number of scalar fields, so we have a much more singular piece, 1 over z to the fourth. And so this tells us that the stress energy tensor is not a primary field. Okay, that's an unfortunate conclusion. T of z is not a primary field. So another way to see that it's not a primary field, well, for example, what I could have done, I could also look at the OP of holomorphic and anti-holomorphic part of the stress energy. So I look at Tz equal of 0. So what's the OP here? Can you tell me what the answer here is? 0, right? Because this guy is anti-holomorphic, this guy is holomorphic. There are no cross contractions, so there is absolutely no way to produce a singularity. So this has 0 as far as singular piece is concerned. But it immediately tells us that's another way of saying that this guy cannot be a primary field. Because if it is a primary field, this guy must always have this piece. Well, actually it does. Forget about it. Doesn't matter. What I said is nonsensical. Anyway, so far we showed that the stress energy tensor is not a primary field. It contains this extra term. And what we can do, we can now use our word identity and ask how does our tensor field transform under general under infinitesimal conformal transformations. So the claim is about OPE implies. So again, what I have to do, I have to construct a current, right? So the current is I d t of z, and I have to act with it on t of z, t of 0, and I have to look at the residues, right? And I have to extract residues of this transformation. So it's clear that in order to get a residue from this piece, I need to how many derivatives? I need to take how many derivatives of b? Third, right? So I'm going to write down the formula. So this transformation of the stress energy tensor delta t epsilon to the -1. That's infinitesimal parameter. So if you do this analysis carefully, I'm not going to do it. We did many similar exercises before. I will find minus d over 12, and then this, as you said, the third derivative, del cube of v, right? So that's come from the first term. That's kind of an anomalous term. And then the other pieces, as we expected for an operator of scaling dimension 2, so this is a factor of 2, and the last piece is just from coming from the shifts. So that's b del t. Okay. So the expressions that we did here is the expression in this particular CFT, which is a scalar field theory. But now we can ask the question, okay? So once people understood that conformal theories are very constrained, so they were asking the question, so what are the most general CFT we have? Suppose I have the most general CFT, and what's the most general form of the stress energy tensor? So alternative way of asking this question, suppose I have a CFT, again, with all this holomorphic, all the symmetry properties as a scalar field theory, but more general. What's the most general transformation of the stress energy tensor? And so the point is, well, so first of all, again, the stress energy tensor would again have holomorphic and anti-holomorphic fields. And the symmetry property pretty much guaranteed to you that it will have the last two pieces unchanged, because those are just related to transformations with respect to shifts and dimension of the operator, right? So remember that this guy secretly has t that's that. So the last two pieces, they are -2 del t minus v del t, right? So each t carries two holomorphic indices. So this guy and v, so this guy has two holomorphic indices. Okay, and when we do our conformal transformation, remember that goes to that plus epsilon times v. So v doesn't carry any index. So which means that this guy, v del t, actually carries holomorphic indices ZZZ, it carries 3 holomorphic indices. So this guy also carries a 3 holomorphic indices. And so in fact, you can argue that the transformation property of delta T must have 3 holomorphic indices, which means that I have to ask, so what is the most general thing I can construct in order to have 3 holomorphic indices? And I cannot take any more which is linear in D, right? It must be linear in D because we are looking at infinitesimal transformations. And the point is, I cannot take any more derivatives of T, right? So if I take an anti-holomorphic derivative, it will vanish because T is holomorphic. And if I take, say, 2 holomorphic, there will be 4 Z indices. Okay, it will transform as an object with 4 Z indices. So the only way to construct additional contribution is by taking our function and acting on it with 3 derivatives, much like we found in that specific case. So there's nothing else we can do. And so in order to do it in general, we're going to write it down as minus C times 12. So I'm writing down this as a transformation of the operator. So this then there are So this is a transformation of operator, and B is parameter of the symmetry transformation. So what can be is that this C in general can be an operator, right? In principle, C is an operator, much like what we have here. We have a symmetry parameter times an operator. In principle, C can be an operator. But in fact, what you can do, you can act on this with a second symmetric transformation, and you can show, which I'm not going to do. So what we can show that del A of C equals to 0, so that C is not an operator. C is a number. So this number is known by a central charge. Of a CFT. It's one of the fundamental classifying principles of all CFTs. See, we ask the question, what's the most general stress energy tensor consistent with symmetry we can have? And so we agreed that it must be of this form. And so the only ambiguity that we managed to leave open was this number C, which is a central charge. Okay, so very good. So we can go back and say, so if we have the most general CFT, what's the OPE of the stress energy tensor it will have? And the answer is simple, right? So we can either use what dynamics, or we can note that C equals to D in the examples that we discussed before. And so it must be true that in general CFT, the OPE of the stress energy tensor out is formed 2z force plus 2z squared P plus So good. So one last comment that I want to make is that what we discussed before is infinitesimal form of symmetry transformations. And we can see that up to those terms, it transforms exactly as a primary field of weights two. And so we can ask, how does stress energy tensor transform under general coordinate transformation? And the answer to that is given by this expression. So finite form for transformation of T. Well, remember that when we had a primary field, So the primary field was transforming in this form, so it was del z prime to the minus h, del bar z prime bar minus h tilde O to O. So now the stress energy tensor doesn't quite transform as a primary field, but it is close to it. And so in fact, what happens is as a transformation property, you can, it's a good exercise, it's doable, you should be able to do it. Maybe it will be in the homework. To actually derive that given this infinitesimal transformation, once you integrate out, there is no plus here, then you will get a finite form, which is this. And then there is minus c over 12. Okay. So what I'm writing here is the transformation under general conformal transformation that goes to that time, some function f of z. So this piece is exactly as you expect for primary field, and then there is an additional piece which is proportional to the central charge, and the combination there is known as a Schwarzian derivative. So what this guy is called a Schwarzian derivative. Okay? And so this Schwarzian derivative is defined in the following form. If I have an arbitrary function f, then the Schwarzian derivative is just 2 del 3f minus 3 del 2f del 2f divided by 2 del f. Right, so one way to check that that's true is to just simply take this general expression and do infinitesimal expansion. So you say that f of z equals to z plus absolute d of z, and you will find out that that thing implies, if you use it, the definition of the Schwarzian derivative substituted here, you will reproduce exactly this transformation properties. All right, guys. So, about 20 minutes left. And so now I have to discuss a bunch of CFTs. And in fact, I have to discuss all these pages, which is unrealistic. At the rate we go, so we go at the rate about 3 or 2 pages per hour. So what I'm going to do, instead of discussing 3 field theories, so now I want to discuss some examples of conformal field theory. So far we had an example of the CFT, which was just mesoscalar fields, right? And it was pretty boring, right? It had everything symmetric, right? Both holomorphic and antiholomorphic. All the weights were the same as holomorphic, in the same antiholomorphic way. So pretty boring. So it's very interesting. Well, it will be important for Fourier string. And so the question is, are there any other interesting CFTs there? And so, which is still kind of simple enough that we can discuss at the same level of rigor. And so that brings us to the topic of 3 conformal field theories. So here, Polchinski considers 3 types of CFTs. One is a linear dilaton. So the other one is BC theory. And then there is another one, gamma beta theory. it's impossible for me to cover all three of them in a way that you, in principle, can ask questions because it's an interesting story. So what I'm going to do, I'm just going to concentrate on this one. So the reason why I'm concentrating on this one is because this is exactly the conformal field theory that will show up as a CFT of the ghost of ghosts in Polyakov action. Okay, so this is important for covariant gauge fixing in Polyakov string. For gauge fixing in Polyakov string. So the linear dilaton one, you can read, it's simple enough. You can read for yourself in the book. I'm not going to talk about it. This one is also very important in string theory. So it's kind of a counterpart of the BC system. So when we talk about superstring, right, we all know that we have to go away from the bosonic string. We have to consider superstring. And then when we formulate a fast integral for superstring, we need to, we have a larger gauge symmetry group, and we have to fix it using both BC and beta gamma system. So that's important for gauge fixing, important in string strings. Okay, and since we are not going to talk about supersymmetric string theory in this course, I'm not going to discuss this, but everything that I am going to talk about BC system, it should be enough. You can literally repeat the words and talk about this gamma beta system. So, having said that, let's do everything we know about the scalar fields. Let's do the same about the new CFT and see some nice property. Okay? And we should be able to make it. So first, I have to tell you what the CFT is. Well, the CFT, so BC theory. So what's the way? How do I know that scalar field theory is a conformal theory? What's a quick way to do it? Well, let's look at the action. DZ bar, del bar Z. Okay? So what's the weight of derivative? What's the weight of the measure? What's dz? What's the conformal weight of the d? -1 and 0, right? So because del z has a weight opposite to dz, right? So del z has a weight +1, so this guy has a weight -1. So this guy has weight what? 0 -1. So this guy, x, remember, has weight 0, and so this guy is holomorphic and anti-holomorphic. So this guy has weight 1 and 1. So the quick way to see, it doesn't guarantee yet that you have a conformal field theory because it comes with a complicated structure. But a quick and dirty way to do it is that if somebody tells you what are the weights, you can say, okay, are you lying to me or not? Because if you are not lying to me, the action vector is scale invariant, which means that it must have weight 0 and 0, which is the case here. So that brings us to a theory which we can use this dirty method to declare that it's scale invariant. So it's 1 over 2 pi e to z. I'm going to write down it as b del bar of c. Okay. So B and C are our fields, right? So B is B of Z bar, same C of Z bar. Except that right now our B and C are not bosonic fields, they are fermionic, which means that BC equals minus CD. So every time we flip the order, we have an additional minus sign. Okay, and there will be, as you will see in a second, there will be subtleties associated how we form normal ordering and cross contractions and all that stuff. So,
do they carry space-time indices?
no, they don't. So, so it's D and C, and so I'm going to declare, the field that those fields B and C, they carry only holomorphic weights. They don't have anti-holomorphic weights. So in particular, I'm just going to declare that my field B has weights HB0, and my field C has weight HC0. And what I'm going to do, I'm going to say that HB equals to lambda. Okay? Pretty much by hand, I'm saying I want to come up with a stress energy tensor, right? Because it is a stress energy tensor that will determine me what are the weights of the field, so that at the end of the day, the field B will carry only holomorphic weights and molar weights lambda, where lambda is any number, and HC is going to be equal 1 minus lambda. Now you can see immediately that I didn't lie to you, that at least naively it passes the silliness test, right? Because the total conformal weight of this object is what? So I have lambda plus 1 minus lambda, so it's 1, so it carries a holomorphic weight of 1, and then there is 1 del bar, so that's an anti-holomorphic weight 1, and so the total action is invariant on the scaling transformation. Okay? So let's continue discussing, and you can see that I can make sense of this theory. Again, it looks like a free theory with any number lambda. Okay, lambda will be an arbitrary parameter. Okay? And so this is a good example where you will see the fundamental property of the stress energy tensor. I will pretty much at some stage define what I call stress energy tensor in this theory. And once I know what the stress energy tensor, the weights of all operators are determined by OPs. So before we go into that, of course, something that I cannot change, and that's the path integral formulation of this theory. Before we go into deriving all this sport dynamics and all that stuff, let's just look at the equation of motion. So if I have the action, and if I vary with respect to B, I have to have 0. So I will have del bar of C equals to 0. And then the second thing, I have to derive an equation for C, for B. So I vary the action with respect to C. And it's clear that after integration by parts, I will get del bar B equals to 0. So those are classical equations of motion, right? So in particular, they tell us that C is holomorphic and B is anti-holomorphic. And so now we go ahead and develop our normal ordering. And so in particular, the first thing we want to do, we want to derive something called P's. So let's look at this path integral. So I have dB dc, so I have to integrate over my field space. And a path integral of total derivative must vanish, so I have delta over delta c. So here I have e to the minus s times c. Okay. just looking at this particular combination. Again, I'm simply repeating everything that we did before. Well, so there are two things I can do. So the first one I can differentiate. So this guy, I can differentiate C inside the action, right? And so when I do that, so let's see what will happen. So first of all, I need to take a derivative of minus S. So there will be minus 1 over 2 pi, right? Now I have to take derivative with respect to C, but C is a second operator, so I have to move past B, and when I anti-commute, there will be a minus 1 there, right? And then I have B, but I have to compute delta of delta C over delta C, right? So I will have a derivative, so I have to integrate by parts. Integrating by parts gives me an additional minus sign. So I have minus 1 over 2 pi minus minus. And so once I integrate by part, I will have del B, right? So that's what eventually will come up, will be left from the action. And then I have to multiply it by this C, right? So I have del bar B times C. Okay, so that's when this functional derivative acts on e to the minus s, and then I have to act on C, and that gives me a delta function, delta 2 of z bar. Okay, so we derived the quantum equation of motion for the product of the operator, and so for this equation of motion. Tell us that del B bar C equals to 2 pi delta function z bar. Okay? So notice that this delta function again is purely quantum effect. See, classically, del bar. Classically, B is a holomorphic field, so del bar B must vanish. Okay, and we are finding that it does vanish except for this delta function. And so now we can do, as in the scalar field series, so what we can do, we can introduce normal ordering. And so the way I'm going to introduce normal ordering is the following. So I'm going to say that normal ordering B of Z1, C of Z2, okay? So it's going to be equal to B of Z1, C of Z2. And then I'm going to subtract minus 1 Z1, 2. Okay? So the logic of introducing normal ordering is such that when we act with derivative, for example, del 1 on normal ordering, B of Z1, C of Z2, I want to get 0. So there are no, so it's like satisfying classical, actually del bar. I have to add this del bar. So it satisfies the classical equation of motion. Same philosophy as we did in the context of scalar field theory. And so in order for me to show that that is the case, I have to show you that so this will be true provided the del bar of 1 over z equals 2 pi delta function. So if this is the right statement, then you can check that the derivative of that guy gives exactly this delta function, which is being subtracted when they differentiate 1 over z. And so the way to do this is to, again, use our Cauchy theorem. So del bar 1 over z. So you can write this down as an integral of del bar of J z bar. And I can go into an integral. So this is an integral which includes 0, right, along the disk. So now I go into an integral around the boundary of the same unit circle. I'll have gz bar dz. So it's going to be equal minus an integral around the boundary dz z. Sorry, what I missed is that there is an I here. There is an I here, so I have minus I to pi I, which is 2 pi, and that's exactly what will happen on the right-hand side when you integrate the delta function. Okay, so so we derived our subtraction, right? And so no contraction, and now we can just literally repeat everything. The only thing is that we have to remember that B and C are not commuting, and so in particular, well, so BC is 1 over Z12. But in fact, what's happening is that C1 B2 is also 1 over Z12. The reason for that is that here you get a minus sign, right, because you anti-commute to field, but you get also a minus sign because you flip indices, right? So here it was Z1 minus Z2, here it will be the same. So the simplest OPEs are symmetric with respect to permutation of the TSBs. Okay, guys, so this is important, and I really don't want to screw up with this system. So what I'm going to do, I'm just going to show one more fact, and we'll continue with BC system. Unfortunately, we'll not end it today. So now, so we see that there is a non-trivial OPE when I take B and C, and now I'm going to we're going to show now that BB is actually non-singular. So it's order Z12, and then CC is order Z12. So there is no, the singularity can never come when we contract or subtract same fields. Okay, so how do I do this? Okay.
Shouldn't that be the accuracy derivative on Lagrange? Because you don't even have a kinetic term of B and C.
Well, we have to be careful, right? Especially from Lagrangian. From Lagrangian, this guy also doesn't have to.
But you still have a kind of term.
Yes, but yeah, presumably it's related. But the easiest thing is we can always derive it, right? So I'm going to show you the good thing about at least the Polchinski book is that you don't have to assume anything there. Everything that he writes can be derived. And so in particular, he makes that claim, and so this is what we're going to do. So the way to do it, we're going to look at this path integral, delta over delta B, and then here I have x minus s times c. Okay. So again, this path integral must be 0. Okay. So I want to compute what it is. So remember that our action is 1 over 2 pi integral d2z, and then I have b del by c. So when I vary this guy, so the only contribution will come from variation of the action, right? There will be no delta function here because B and C they're just different fields. And so when I vary the action, what I will find out, I find out del by C times C. Okay? And so you can see the fact that the path integral must vanish implies that this is 0, which implies that the del bar CC must vanish. So the product of two C operators satisfy satisfies the naive equation of motion. And you can play around and show that the same holds true for the B field as well. So we'll stop here, and so next time we will write down the stress energy tensor for the theory, and we'll confirm the facts about the weights of those fields.